me give a brief introduction of who our speaker is. He received his Bachelor of Engineering in Engineering Physics from McMaster's University and a PhD in Astrophysical Sciences from Princeton. He's a recipient of the Natural Sciences Engineering Research Center postdoctoral fellowship sponsored by the National Research Council of Canada and the National Science Foundation Presidential Young Investigator Award, and both the APS John Dawson Award for Excellence in Plasma Physics and its Arthur C. Lashlow Prize in, pardon?
Shallow.
Shallow.
Arthur Shallow.
Arthur Shallow Prize in Laser Science. He's a fellow of the American Physical Society and the Optical Society of America, and as well as a University of Maryland Distinguished Scholar Teacher and Distinguished University Professor. So let's welcome Dr. Milchberg.
Thank you very much for inviting me, and it's a pleasure to be here. In fact, very convenient, right across the street. Once you make your way through all the construction and purple line construction, everything else. Anyway, so your introduction told me that I've chosen the correct talk to give. I have two versions of this, a more introductory talk and a talk that actually, less introductory, gets into it much more quickly. But when you said you didn't know lasers could accelerate particles, that told me I picked the correct talk to give. So I'll talk about that. I inserted a couple of words into the title, multi-GeV, because that's what we've accomplished over the last couple of years.
Okay, just a comment. I mean, you're using laser to accelerate.
Yeah.
Some years ago, we had talks on laser cooling.
Aha.
Now we're pushing the other way.
Right. The idea, though, is actually to have beams that are very high center of mass energy, but don't have a big thermal spread. So in some sense, you want them to be thermally cool, for accelerator purposes. You don't, as you'll see, the beams that we generate, I'll show you, are not exactly ready to do high energy physics. They're not sort of narrow energy spread. It's like a shotgun blast, but it's very high energy. And it's sort of the first time that lasers have been used to accelerate particles to this kind of energy. So the talk will be basically all the background that you and delivered sort of very qualitatively, I think, but you'll sort of have an understanding of how the laser can do this kind of a thing. The funders are listed there at the bottom. I won't get into the details of who funds what. So next slide is basically all the people, all the acknowledgements. So over the years, many students in my group have participated in sort of building up the science that led to the results I'm going to show you. The folks with the red asterisks are people who are in my group right now. They're not all working on this project, but my group does 4 or 5 different kinds of research, not including laser acceleration. And the laser acceleration people in my group basically steal people from doing other things, people doing simulations, or they may have a scope or a diagnostic, or they discuss things with them. So everyone's sort of involved in this, collaboratively. And then I have collaborators outside listed up there on the right-hand side. The main collaborator on what I'm going to show you here is Jorge Roca at Colorado State University. We actually went over there to do some of these experiments. So the 10 GeV were not generated at Maryland. They were generated at Colorado State University using our techniques. This was a project actually funded by DARPA to generate muons with electrons. So what I'm going to talk about right at the end of the talk is applying these high energy electrons to generating muons. DARPA was interested in using muons as a source for imaging. And this was a project, there are 2 groups actually doing this project, one at Livermore and one at Lawrence Berkeley Labs, and we're collaborating with both of them. So the main collaborators you'll see that on this work are Colorado State University, which provides the big laser we use, and then groups at Livermore and Berkeley. That's good.
I think if you just hit the meeting is being recorded, okay, on your screen.
I don't see it on
You
my
don't
screen.
see it on your
Wait,
screen?
wait, I already did it once. There we go. Okay. All right, now we're good.
No, well,
That's not a touch screen.
I don't know. It's not blocking anything now. but
Okay, let me move this.
I don't know if that's on you.
Okay,
Ours.
yeah. I don't know.
I don't
Always
see
something
it
with
on my
Zoom.
screen. It's not on my screen, so we get the whole screen.
This is all in the background annoyance. Right. So anyway, let me go to the next slide. This is just pictures of my guys out at Colorado State University. That's the chamber we were working in. The three lead people on this experiment from my group are Bo, Ella, and Jaron. Jaron on the right is a big fisherman guy. I think he took Bo and Ella hostage to go fishing, somewhere there in Colorado. So I'm going to start with sort of our main exciting result and then sort of work through the details, building it up, showing you where this came from. If you're interested in a sort of a lay person's description of what we've done, we had a Physics Today article last year. So take a picture of, you'll get the slides, I guess, at the end of this talk, so you can look this up. It was actually one of these quick studies. I don't know if you've seen those things at the back of Physics Today. So
Yeah, it was in the back.
right in the back, near the back. So we had to summarize everything we did and make it very clear for those things. You don't have a lot of space to sort of confuse yourself or the reader. Right. So anyway, so the story here is this is a vacuum chamber. The green light you see there is from some of the lasers that are on. I won't get into the details of how these lasers work, but the key points here is that there is a pulse whose peak power is 300 terawatts. I'll give you a scale for what terawatts means in a minute, but basically, power is energy divided by time. So the way you get high powers is basically to make the time interval short, right? You don't have unlimited energy, but you do have tricks for making the time interval short. And energy is expensive. So generally, the higher the energy of these laser systems, it sort of scales somewhat with energy, whereas it's much cheaper to make the pulses short. And what you need for these things is high intensity. You don't necessarily need high energy. So I'll talk about what the energy.
Okay, so the laser is pulsing.
What?
The laser is pulsing.
Pulsing. It's a pulse. Yes. Yeah. This laser runs at one. It runs at 1 hertz nominally. We run at much less than a hertz for several reasons. One is radiation hazard. This interaction generates a lot of radiation. The other is we use a pulse gas valve. So if you look at this picture here, I guess, can the people see my cursor moving around here? Can you see my cursor up? Can you see my cursor?
Right
I
there.
can't see the screen either.
Let's see.
I do.
Wait, let me do it.
We can't see it
my
on
cursor.
Zoom.
See my cursor. You
okay.
can see it right there. Yeah, you can see it.
Okay.
Okay, so this thing I'm pointing to now is a 20 centimeter long gas jet. So this shoots out a supersonic stream of hydrogen in a sheet all along the length of this thing. And basically what we are generating where it says prepared index structure is a plasma waveguide. It's not completely ionized, but it is partially ionized. It's sufficiently ionized so that when a 300 terawatt laser pulse goes in along this red arrow, it generates its own waveguide as it propagates. So this is this thing is like an optical fiber. And when it enters, this is sort of what happens afterwards. This bright strip you see here is basically hydrogen plasma that's basically lit up by a 300 terawatt laser pulse that's propagating along it. So this thing is actually propagating along an optical fiber made out of plasma. And this is one of the things this is one of our innovations. This is actually the key thing that leads to these very high energy electrons, which I'll talk about. So think of this as like a regular optical fiber. This thing's actually thinner than a human hair. The thickness that you see here with this brightness is just fluorescence. But the actual structure in which the 300 terawatt pulse is propagating is, less than 100 microns in diameter from side to side. It's very, very small.
That has to do with the focus of the filter, focus of the pulse. I mean, you've got a very narrow.
So the focus is 25, it's f25. So the spot size the beam is something like 30 or 35 microns. That's the 1/e² intensity radius. So you try to match that with the optical fiber, right? So
Right.
you have the optical fiber has a mode and the focused laser has a mode. You try to match it, because if you don't match it, you will get an inefficient coupling, or you will generate either inefficient coupling, or you could just generate a bunch of high order modes in this wavelength. The thing is literally like an optical fiber, except it supports intensities 8 orders of magnitude higher, and then would destroy a regular glass optical fiber. Why? Because it's plasma already. You can't destroy anything any more than that. So it's already destroyed. If you're interested in all of this kind of thing, as I said, read the Physics Today article for a brief, I think, fairly clear explanation. And then there's other papers shown here on the bottom right. So I'm going to explain how all this stuff on the right works. And I hope I'm supposed to go an hour, and I know I'm already sort of, losing time here by sort of talking too much. So here's like the brief outline. I'll give some history. I'll talk about electron accelerators. Then I'll explain how you get it. We got laser electron acceleration up to about 10 GeV, and then I'll talk about the muon generation thing I was mentioning earlier. Okay, so this is a busy graph, but basically this is the history of lasers. 1960 was the first demonstrated laser. That was Theodor Maiman. That was a gain switched laser. And a question? I can't hear anything. Should I? Oh, there's feedback. Okay.
I just muted him.
You can see the screen.
I got that.
Yeah.
Are we getting an echo here?
Getting feedback. Oh, it's fixed.
Is that
Somebody's-
better? Yeah.
Yes, that's
We
better.
had one guy who was.
Yeah, somebody had their speaker and microphone or something. Okay. Anyway, this is the history of lasers. In one plot, you can see the bottom axis is a year. The first laser, as I said, is 1960. And you can see there's an arrow saying CPA, and there's like a knee in this curve. This is around the mid to late 80s. It turns on. In fact, the 2018 Nobel Prize was given for this knee in this curve, basically having this curve shoot up. So you can see the power automatically goes up very rapidly over the years, logarithmically, exponentially. And the region we're operating in for these laser acceleration experiments is this green area called relativistic optics. The way to think about that is when you're in this green region, so you can imagine, an electromagnetic field. You have an electric and a magnetic field in the wave. You're wiggling think of a free electron. You're wiggling the free electron. Just think about the electric field part of it for a second. You're in the relativistic regime where you're wiggling that electron at nearly the speed of light.
Cool.
And in fact, it's very, very close to the speed of light. And any extra energy you put into it just goes into the gamma factor.
But when you say wiggling, how do you wiggle at the speed of light? I mean, wiggling is a oscillation, isn't it?
Yeah, wiggling's an oscillation, so its peak at its peak velocity.
Okay.
Of the oscillation, it's near the speed of light. Then it reverses, goes through zero. It also turns out that when you have a very intense field, the B field is also large. So V cross B over C, right, is of order in size of the electric force. And so you also have, it turns out you get forward motion. So it's not an up and down wiggle, it's a figure 8 motion.
Okay.
Because the B field is actually causing the forward and backward motion. Okay, so let me go to the next slide. Okay, so what's a terawatt? Let's talk. A terawatt is 10 to the 12 watts. The average electrical power consumption is 2022. I got this off Wikipedia. Hope it's right. Was 3 terawatts. And then all sources, all kinds of engines, motors, whatever else, fossil fuels. It all adds up to 18 terawatts. The US electrical was half a terawatt in 2022. So that tells you what a terawatt is. So it's not that these lasers that are 300 terawatts these are steady state powers here that I'm listing here. These are just average powers, whereas I'm getting 300 terawatts by packing a finite amount of energy into a really short pulse. Okay, but that tells you what a terawatt is here. This is the landscape in the world for lasers of this type. So this is lasers greater than 10 terawatts in 2009. And that sparked some, reflection in the US community, the laser community, the plasma physics community, the optics community, about US falling behind, because there's a lot of facilities out there in Europe and Asia. But in 2020, this was part of the sort of analysis of what was going on. You can see in Europe and Asia, there's just way more than in 2009. And there's more in the US too, but not, the ratio isn't exactly the same. Maryland, I've indicated here with the red notations, Maryland. So in 2009, we actually got a 25 terawatt laser. And as we speak right now, I have a team from a laser vendor installing a 100 terawatt laser in my lab right across the street here. So we will be able to, by middle of next year, we hope, be able to generate at least 1 GeV beams in my lab at Maryland, electron beams. And that is going to generate a whole new set of headaches for our environmental safety. I'm already talking, and headaches for me too. I'm already talking to them about that. And so, as I was saying, I'm sort of giving you the landscape here. So because of this increased activity in this kind of research, intense lasers, National Academy report which basically said the US is falling behind. So if you're interested, you can. Okay, so I have a ton of slides. Let me actually skip through a few things here. I guess this is actually a very important thing. So I don't know how many of you have thought about nonlinear optics, but basically, prior to the invention of the laser, most optics was linear. That is, you could actually view an atom. The electron cloud around an atom is like attached with a spring. And then you turn on the electric field, and the dipole response of the atom is more or less proportional to the electric field. But with the laser, the electric field is larger. So you are now stretching the spring to beyond its linear response. And in fact, what happens for most common materials, the spring becomes weaker. And so you can look at this plot in the lower right, you can see the displacement actually starts to go superlinear, right? Because the spring's getting weaker. And that contains a lot of physics. That contains nonlinear optics. So prior to 1960, they're more or less linear. So the way to think about this, again, there's not a lot of physics in what I'm showing right now. It's just perturbation expansion. But you can say that in Maxwell's equations, one of the source terms is the dipole moment per unit volume, which is capital P. It's the polarization. You can expand that in powers of the electric field. You can get rid of the square term because it doesn't change sign when the electric field changes sign, which you want. You want the polarization to follow the sign of the field. So you got to get rid of that. And so you actually have the two lowest non-vanishing terms are linear and quadratic, or linear and cubic in the field. So this thing in front is almost like a susceptibility, right? P is chi times Z. So it's like a susceptibility, but susceptibility depends on the electric field. Anyone who's done nonlinear optics recognizes this expression. This is like the effective index is the low intensity index N naught plus this thing which has this N2 coefficient. N2 is called the nonlinear index of refraction. I don't know if you've ever heard about this, but this is basically saying the refractive index is intensity dependent at the lowest order above linear. So what that says is that if you have a pulse that looks like this, so this is a pulse, so this is the intensity profile, so it's a bell-shaped intensity profile with flat phase fronts, and you propagate it, the phase fronts actually will lag because the index is higher in the middle, right? Due to that effective index. The index will be higher in the middle just due to this N2 times E squared term, or N2 times intensity. So you'll get self-focusing. And in fact, in the 1960s, when they first started amplifying substantial laser energy in rods, this effect was actually happening inside rods. So in other words, the intensity was high enough in these expensive laser rods that the beams basically formed their own lens as they were propagating and just collapsed and caused a spark, a breakdown plasma basically inside the rods. And that spurred a big subject and everything else. So everyone was sort of aware of this self-induced damage when intensity gets high. So this is actually a reflection of the success of the laser. We have enough intensity now that we are causing a pulse to generate its own lens as it propagates, and it'll collapse and self-destroy, the medium that it's propagating in. So this is what led to
But when it collapses, it goes to nothing?
No, that's an excellent question. Actually, a lot of my research depends on this. So mathematically, it would go to a singularity, right? Because what happens is as the lens forms, the beam focuses. As it focuses, it gets more intense. The lens gets stronger, and it focuses even more. But there's always something called a collapse arrest mechanism. Some physical thing stops it in the end. So in the case of destroying laser rods, a plasma forms when you ionize the bulk of the medium, and a plasma is like a negative lens. So the beam goes in. Once it makes plasma, then it tends to blow out again. It refracts from the plasma, so it's self-limiting. There's another effect that we've explored. It actually happens all the time in the laser acceleration game. So if you have something that's already plasma, so let's say it's a fully ionized hydrogen plasma, just a bunch of protons and electrons, and you send a beam like the one I showed in that slide into that thing, then what happens is you get the same self-focusing effect. The nonlinearity is the cap on the velocity of the electrons. So if you dial up the laser intensity, and you've done that in the center, the wiggling electrons get close to the speed of light, and they no longer execute sinusoidal orbits. So they're close to the sinusoid when the field is passing from negative to positive, right? Or I guess it's pi out of phase. Pi by 2 out of phase. So near the peaks of the velocity, they can't go all the way to C. In other words, it's going to be like a flattened sine wave near the top. And that's a nonlinearity. You can expand that the same way that I just did that perturbation expansion. And then what happens is the beam collapses, but you've already ionized. So you're not going to, so it turns out the light pressure is high enough. It just pushes electrons out of the way. So you have no longer any nonlinear medium at the collapse point. So the self-limitation of this is the light pressure, because it just pushes when it gets high enough, it pushes the electrons radially out of the way. Are you following me on this? Mm-hmm. Yeah. That's one way of generating a plasma wave, which is something I'll talk about. Anyway.
Now the plasma wave is going away from the beam, not along the beam, right?
In that case, yes, but it also goes along the beam.
Okay.
It's a 3D disturbance.
Okay.
In that case. Okay. This is the Nobel Prize from 2018. So this is all about getting really, really short pulses. And the way you do that is you start with let's call it an oscillator. This is the brains of the operation. It generates a pulse that has a bandwidth and a phase and stuff like that. I won't get into it. It's a mode-locked laser. If you've heard the phrase mode-locked, it's a mode-locked laser. Mode locking was invented in the 60s as well. Now these pulses are very, very short. but you don't just send them through the amplifier directly. So I'm not going to take this thing that the arrow's on and send it into the amplifier because it's going to destroy the amplifier, right? Because the intensity gets high enough and it's going to self-focus. So what you have to do is make it really, really long. And the way you make it really, really long is you use a pair of gratings. So you can actually convert this thing, which may be, let's say, 50 femtoseconds long, which is very short. You could convert it into something that is, let's say, 1 nanosecond long, right? So this is you stretch it by a factor of more than 1 million in time. And when you've stretched it, its intensity drops so that when you amplify it, it doesn't destroy the amplifier. And then after it goes through the amplifier, you reverse the process with another pair of gratings. Or what people do, because gratings are expensive and you want to have the same setup, but just reverse the beam through it and flip the beam, then you just use the same pair of gratings, but you just have a roof prism. You bring the light down, you go back the other way. If any of these things are clear, but these are optical tricks. This is what the Nobel Prize was given for.
How do you amplify it? Somehow you have to give it energy, right?
Amplifier. The thing that called.
Yeah, but I mean, how do you?
Oh, how is that thing energized?
Yeah, how do you feed the energy to the?
With another laser.
Oh.
So the most commonly used ultra short pulse laser now, at least for scientific purposes, is the so-called titanium sapphire laser. It's a sapphire crystal with titanium, doped with titanium. And basically, it has a very big bandwidth. And so you use a green laser, either a green laser or a glass laser. So it's a green laser. It could be frequency doubled YAG or frequency doubled glass. So this is the sort of laser technology.
So if you give this other laser, the two lasers combine somehow?
No.
To one pulse? That's
no. So okay. So look at this picture. This is the amplifier. The laser is just an energy delivery. The green laser is separate from this.
Yeah.
There's a beam coming from a different direction.
Okay.
It's an energy supply vehicle for the amplifier.
okay.
That's all it is. You can think of it as it's like boiling
But
water.
I guess I'm asking, what's the physical principle? How do you take one electromagnetic pulse and somehow give it?
Okay.
A
The amplifier has an absorption band that includes green. And so what you're doing is you're pumping excitation from the ground state into the upper level of a gain transition inside the amplifier.
Okay, so the amplifier is actually a solid of some sort.
It's a solid, it's titanium. It's a sapphire crystal.
Okay,
Sapphire crystal
so
with titanium ions.
the one laser comes in, and I guess it starts to excite electrons, which in turn emit
It
again, but they'll do it with a higher energy.
It excites titanium ions in the crystal.
Okay.
It excites titanium.
Right.
It excites electronic transitions in titanium.
Okay.
That's your energy storage.
Okay.
Actually, you're exciting what's called a population inversion. Have you heard the phrase population inversion?
No, I mean, this isn't right.
Yeah.
Okay,
So what you're doing is you're investing green energy
yeah.
from this other laser, which is just an energizer laser.
Okay.
Any green, which it has to be a short pulse though. So it's not wow, it's an impulsive excitation. The green pulse is approximately 5 to 10 nanoseconds long. It's very short.
Okay.
It's not as short as this, but it's because we're talking femtoseconds, but it's short. All this green energy goes in and it excites titanium ions.
Okay.
And it excites from lower to upper. That causes what's called a population inversion.
Okay.
Then photons come in from this ultra short seeds pulse, which has been stretched. And those are the seed photons. So what happens is you have stimulated emission in the amplifier. I should give a separate talk on lasers.
Okay. And since it's energized from
the green
laser, it comes out with more energy
than came in. The amplifier has stored energy in it, which has been invested in it by the green laser.
Laser, okay. As opposed to somehow combining the two lasers.
As just a little history thing, I mentioned Myman, the first laser demonstrated in 1960. That was actually a ruby crystal. And the way that was energized, he got a helical flash lamp from Kodak. They actually made these things, just off the shelf helical flash lamp. You know what a flash lamp is, like in the old cameras used to use? So they ran a pulse of electricity through this helical flash lamp, and the broad white light from this intense white light from this flash lamp, the ruby rod was inside the helical flash lamp. The broad white light went in, it was absorbed by the ruby, and you got a population inversion very rapidly, actually, and a bright red beam shot out the end of the ruby rod.
Okay.
There was actually a mirror on one end of it. Okay. I can come back and give a talk on lasers.
No, I was there. I usually go to the physics colloquiums.
Yeah, I've seen you there.
Right. And I remember your talk, and I always wondered, well, what is this quote amplifier? So this is my field or anything. So I wasn't.
I will say, and actually, I don't know if any of you know anyone who are looking for a graduate school sort of project or anything like that, through friends or anything like that, but. The work that I'm talking about is hugely interdisciplinary because you have to understand, what the application of the laser is. That's mainly what I came to talk to you today about. But you also have to know all of the physics that underlies the laser too. So it's a tremendous education for the students. Okay, this is a picture of a laser. I'm going to skim through it quickly in case you get too interested. All right. So now I talked about power. Let's just talk about time. What does a femtosecond mean? So basically, the classical circulation. If you were to work out a classical circulation time for an electron going around an atom, it's about 1 femtosecond, something like that. And then in a macroscope, in a sort of a cooperative kind of medium like a lattice. The collective oscillation, or the phonon timescale is about 100 femtoseconds, something like that. So you can see immediately why. It's that femtosecond lasers are used a lot to do time resolved measurements in solid state because you can get pulse lengths that are actually less than the phonon, period. And then if you were to shine one of these lasers across the lab, one of these pulses, it would be really short. It would be, let's say, for 100 femtosecond pulse, it would be about a 30 micron long disk of photons coming at you. And for 50 femtoseconds, it would be 15 microns. And it has a very high energy density. So that now you would see it if it was a 10 hertz beam. It would look to you, it was scattering off moisture or dust. It would look like a continuous beam. But it's really a beam, pulse like this, a pancake every 100 milliseconds, if it's in 10 hertz. And then you focus the pulse. Typically, if you focus the pulse, use a lens. But for these kind of intensities, you wouldn't use a lens. You would use a parabola, only all reflected optics. But the point is that this region of high intensity here is at most 100 wavelengths or something like that, which makes it, in the few millimeter range, typically for high intensity or less. So basically, you can get high intensities with these lasers if you focus them, but the focus is just not very long in the longitudinal direction. It's not extended. And what we want to do is extended, which is why we developed the waveguide that I talked about in the first slide. Here's some numbers. So this is intriguing. If you were to take one of these typical lasers that are around today, and they range from university labs to national labs, and you were to focus them, you would get between 10 to the 18, 10 to the 22 watts per square centimeter, which seems very, very high. It is very, very high. At 10 to the 18 already, if you exposed a free electron to that kind of intensity, the free electron would be wiggling at basically the speed of light already. So it turns out our experiments are running at about 10 to the 19. That's what I'll mention. And if you were to work out, if someone gives you a peak power for a laser pulse or any electromagnetic pulse, you could use Maxwell's. Right. Intensity is in Gaussian units, right? It's C over 8 pi times E squared. I don't know if you remember this formula, but basically the intensity is proportional to the square of the electric field. And so if I give you an intensity, you can extract the electric field. So it turns out at 10 to the 19, the electric field is about 50 gigavolts per centimeter. Okay. So you should be very excited because you can think, wow, all I need is one of these beams and I will generate 50 GeV electrons in 1 centimeter. And if you remember what SLAC was like of order 50 GeV, 50 gigavolts acceleration field sustained over 3 kilometers. You needed 3 kilometers at SLAC. Here you get it for a centimeter. So there's a problem, but there's a problem with this. I'll skip through that. Let me skip through this. Okay, so let's say I take one of these lasers and I focus it into a gas. All right, so here's I drew the gas sample. It's like a sheet of gas, and here are my gas atoms, these white fuzzballs. Well, the very leading edge of the laser pulse, as it goes into the gas, it ionizes the gas, and it turns it into a plasma. The prior slide that I skipped over very, very quickly just explains how the ionization works. The laser electric field is so high, then the electron just basically tunnels out of the hydrogen atoms, if this is hydrogen. So this thing basically ionizes almost instantaneously. And so you get this hot gas. For the pulses that we use, we're closer to 10 eV. I call, in the plasma physics community, people don't call 10 eV super hot. They call that warm, even though 10 eV is 100,000 degrees. They call that warm. So that's sort of what we get. I'll talk about why. Okay, so now let's talk about accelerators, why you might want accelerators. This will explain the GeV, the interest of the GeV scale, or at least historically. So this is basically, I find it useful to think about accelerators as microscopes, because if you want to see something that's really, really small, you need a very, very small wavelength. And de Broglie, the relation between wavelength and momentum, right, is to get a small wavelength with a very high momentum, right? Lambda is h over p, right? That's the de Broglie wavelength of a massive particle. So to get a short wavelength, you need a very big p, big momentum. If you have a big momentum, you have a very big energy. So that's why accelerators need these really, really big energies, because you want the wavelength of their particles, which you can view as probes of your target. You want them to have very short wavelengths. So that basically sets the scale. So this is a bit of an historical thing. This is sort of a oversimplified cartoon of the discovery of quarks. So they were looking at protons, and if protons were smooth, if they had a smooth mass distribution, you would just see small angle scattering. And that proton has a diameter 10 to the minus 15 meters, something like that. But if you have some structure internal, you would not have small angle scattering, you'll have large angle scattering. But the question is, what kind of wavelength do you need in your electron microscope to examine an object that is 1 femtometer in diameter, of order 1 femtometer in diameter? It turns out you need something substantially bigger than a GeV to do that. That is what you need if your wavelength is going to be less than the object size you want to look at. So that sets the GeV level. And here's the experiment. This was done at SLAC, and they used 20 GeV electrons, and they saw large angle backscattering. So that said that there was some, substructure in there that looked like, seeds in an apple or something like that. Okay. Anyway, this is a plot. This is a well-known plot called the Livingston plot. Basically, this says as you go up in energy, or as years go by, It seems like it's somewhat diminishing returns using conventional technology because these curves all sort of level over and the price tags associated with them are going up. And, that exposes you to political considerations, testifying in front of Congress and stuff like that. And it's, because it's very, very expensive. So there is an effort, and my group's been part of it for a while now, to look for cheaper ways to accelerate particles. There's a debate about whether the methods that we've come up with, my group and other groups, are appropriate for high energy physics, because the quality, you need extremely high quality beams for high energy physics. And this is still, there's been a lot of progress in the field that I'm in, but it's still not clear whether one would get the high quality beams that you need that you use in conventional accelerators. But the energy elements, as I'm going to talk about, are looking very good. Here's an updated same plot. I'll skip through that. Okay, so let's talk about how you accelerate electrons. Just to remind you, this I keep showing at the talks I give, but a few years ago, all of us had CR capital tubes, and that's basically a particle accelerator, a 10 kilovolt particle accelerator. My favorite TV show is from being a kid on there.
Accelerator, yeah.
And so basically this basic particle accelerator has the three parts that even the bigger accelerators have. There's a source of electrons, there's an accelerator section, and then at the end you move the beam around. And so all of these pieces map onto SLAC. SLAC is basically now used as the for a X-ray free electron laser called LCLS. So it's been decommissioned as a sort of an accelerator tool for energy physics studies, but it's still being used, which is another application of what I'm doing: free electron laser seeding. Anyway, SLAC is the same thing. It's 2 kilometers long. The thing that I didn't get into, or maybe I will, I guess I will next. Okay, why is SLAC 3 kilometers long? It's because the accelerator structure is basically a bunch of copper pipes. And to accelerate something, you need large electric fields. But if you're doing it in a copper pipe, you have to keep your accelerating fields below some level, or else they're going to induce breakdown in the walls of the tube. This is a material structure. And the breakdown is, there's still lots of studies in this, but it's between 10 to the 6 and 10 to the 7 volts per meter. So that's your maximum field, because if you drive it higher than that, you're going to get lightning basically inside the copper structure. And that means that if you want 50 GeV, you need 3 kilometers. Basically, you have to sustain this acceleration over a long distance at this reduced field. If you want to have a smaller structure, you need to drive the field way up, okay? But it can't be in a copper structure. In fact, what could it be in? Let me skip through this. Okay, let me skip through some of this stuff. Okay, actually, this is important. Remember I showed that for a laser beam, you could get, for a 10 to the 19 watts per square centimeter laser pulse, you could get 50 GeV or 50 gigavolts per centimeter. That you can't for multiple reasons. One, the field is 50 at peak. It is 50 gigavolts per centimeter. But can you use that to accelerate particles? No, for a couple of reasons. One, that near the focus of the pulse, the beam sort of looks like a plane wave, which means that the E and the B are orthogonal to the propagation direction, and you want to accelerate in the propagation direction, because if you accelerate sideways and the beam's going that way, it's just lost. You're not experiencing a sustained field. The other thing is that if the electron starts from rest, and yes, it will get up to nearly the speed of light near the peak of the pulse. This is the second cartoon here. But then it will just re-radiate the photons back into the laser pulse, and it'll return to rest. There are funny tricks you can do. And there's been a lot of papers on this that, well, what if you have, 1.5 cycles? Then you're not averaging out the swings, or what if you send the electron in at a funny angle, but you don't get much. So it's really essentially zero. Okay, so the problem here is I just listed it, a couple problems. The other part is this, that these high intensities are only sustainable over the length at which you can maintain a focus. And that's typically called the Rayleigh range, or the confocal parameter. In other words, light diffracts. Because light diffracts, it wants to spread. A lens defeats the spreading. The lens causes it to go to a focus. But once that's the focus, it wants to spread again. So on the other side of the focus, it just spreads again. So this distance over which it's intense is very short. So when you say 50 gigavolts per centimeter, you're not going to get a centimeter. Okay, so all these reasons conspire. And then there's a final reason. Near any of these materials, let's say like a copper structure or anything else, you generate plasma, because these are really intense fields. You destroy stuff with them. So the thing that actually saves the day is plasmas. And so this is a famous paper from 1979, has lots and lots of citations, and at the time, all of the technology that sort of we're using, and a lot of groups are using internationally to sort of make this happen, didn't exist. So at the time they said, well, if you had 10 to the 18 watts per square centimeter and you had a plasma with an electron density of 10 to the 18 per cubic centimeter, which is about 10% of atmospheric density, something like that, a little less, then you could get a GeV per centimeter. And they work it out there. But everyone was reading this and go, oh, very exciting. But, it was like fusion, it was like in the future. Except laser fusion, I guess, is here to at least is a very nice demonstration. But all of these pieces were the laser especially. But now we have all of that stuff. What we do, so this paper talks about various schemes. The blue dashed one is the one we use. Okay, so let's now talk about if you had one of these lasers, let's say you had one of these lasers and you focused it into a gas jet. Typically, people use helium or hydrogen in the gas jet. It's just the simple atom. You remove all the electrons, or one or two. So there's a high intensity laser going to the gas jet from left to right. So this is what it looks like. This is just the front of the laser pulse going in. And because this light is so intense, even the front of the laser just ionizes everything. So this thing actually, even in the way leading edge of this pulse, it ionizes everything. Okay, is that clear from this picture? And then here's the next thing. You look on the other side, and there is a relativistic beam of electrons that squirts out the other side. Okay, I haven't explained why, but this is observed. So if you take one of these pulses, you send it into a gas jet, and if it's intense enough, you get a collimated beam of electrons squirting out the other side, and you measure that here. So the way you measure the spectrum is you send the beam through a magnetic spectrometer, right? Because their more energetic trajectories are bent less, more energetic trajectories, less energetic trajectories are bent more. And so on some screen, you get a spectrum. And so what happens is, this is the pulse, and I'm going to explain now how acceleration happens. The laser pulse, this is a picture of the laser pulse inside the plasma, okay? Propagating inside the plasma. Now, the jet typically is like the left to right through this puff of gas is typically of the order of a millimeter or something like that, maybe a few millimeters. And the pulse itself is only 30 microns long. So it fits well within there. So here it is propagating left to right. And this laser actually is pushing electrons out of the way. This is so intense that it actually, the pressure from the light is pushing the electrons out of the way. So I've shown that with this accumulation of yellow here. Those are the electrons getting pushed out of the way. Then the pulse is moving, and the pulse is moving at less than c. It's moving at the group velocity, and because it's going through a medium. It's not going through vacuum, it's going through this plasma. So it's moving at less than c. And just past the pulse, there's no more pressure pushing it out, pushing electrons out. So they snap back and they accumulate here. But they overcompensate. They get too dense and then they blow back out again. So this is basically a charge density wave that's following the pulse. This is a plasma wave. Okay, so there's a void where the pulse is. There's an excess of charge where the pulse isn't. And then it oscillates, right? You basically set a charge density wave into motion. And this whole structure is moving from left to right at the group velocity of the pulse, right? This is all just following the pulse. This train of things is following the pulse going to the right. This thing is called a wake field because it's a lot like, you can think of this thing here as like a boat going through the water, and behind it there's waves, except this is a wave in a plasma. Now, the thing here to look for is that this excess of charge here means it's negative, excessively negative. The deficit of charge at the front means it's positive because you've pushed the electrons out, but the protons, which are 2,000 times heavier, haven't moved. They're inertially just sitting there. They don't know what happened. They lost their friends. Their friends just got blown away by the laser. And so if you look, there's a polarity going from minus to plus. And this whole structure just follows the pulse, plus, minus, plus, minus, plus, minus. And then below, I've shown the local directions of the electric field. Electric field points from plus to minus. So this structure is moving from left to right. These fields that I've shown on the bottom are the fields that accelerate electrons. So the laser isn't directly accelerating the electron. The laser has basically set up a charge density wave in a plasma, and it's the electrostatic fields of the plasma that's accelerating the electrons. And we like this because notice that those electric fields are basically aligned along the propagation axis. They're not transverse, like the E and B of the laser pulse. So now you have to say, well, where do I want to, if I have a test electron and I want to put it in this structure and accelerate, where do I want to put it? Well, where you want to put it is basically between the first plus, between the plus and the first plus and minus right here. Because then the electric field is pointing from right to left, but it's an electron, right? So the force is minus QE, which means the force goes to the right, because Q is minus E. So the force basically on the electron goes to the right. A positive charge would be forced to the left, but a negative charge is forced to the right. And you want to keep the electron there. And if the electron sits there and rides with this structure, surfs on this thing, it can get accelerated to very high energies. The key to this is that even with very low plasma densities, even 1% atmospheric, really low, those electrostatic fields are enormous. You can actually work out, it's a very straightforward electrostatic problem to work out. I'll show an equation, you can work it out, but it's really a fantastically large electric field. So here's a picture of what it looks like. So there's the pulse. It's like a one-dimensional picture. The pulse is there in blue. It's moving at the group velocity, which is a little less than c. It generates a positive void, or it kicks all the electrons out, so it leaves positive ions and so on. So these are all the local electric fields. So this is like a 1D version of what I drew in the prior picture. And these are the fields. So the charge density and the plasma electric field go like that. And as I said, if you look on the bottom plot, if you want to get some test particles and accelerate them, you stick them right in that location. Now, something really interesting happens called dephasing. So it turns out that the fields are so strong that accelerate this blob that I drew here, that the blob can actually start catching up to the laser pulse. In other words, you can accelerate this thing in a fairly short distance so much that it actually has a speed faster than the laser pulse. The laser pulse is moving at the group velocity, but it's not vacuum. It's moving at slightly less than c in a tenuous plasma. So for all intents and purposes, you would just say it's just moving at c. But these really small differences matter. And so once this electron starts moving faster than the laser pulse, it actually moves to a decelerating part of the field. You want to be always in a location where this pink arrow at the bottom is locally pointing to the left. But if you move a little forward, you will actually have it going the other way, and you will slow these things down. Now, here's a simulation of what it really looks like. So I don't know if you've heard about molecular dynamics calculations, and I know there's something called particle and cell codes, where you're actually calculating F equal ma, or actually better, not really F equal ma, you're doing F equal dp by dt, right? That's relativistically correct. F equal dp by dt on all the particles. And what is the F? The F is the Lorentz force. It's QE plus Q over CV cross B. So you're moving them around and you're solving Maxwell's equations. Because as you move the particles around, you're changing the charge density, you're changing the current density, and those are the source terms in Maxwell's equations. And you're solving that whole set of equations for this thing. And that's why we have a high performance computer time that we get in my group, so you need supercomputers to run these things, and so these are just kinds of simulations we do. It's very hard to get analytic formulas. This is maybe the more specialized stuff, but there is this thing in an E&M called the normalized vector potential. You may remember capital A is the so-called vector potential. You multiply it by the charge of the particle you're thinking about, in this case electrons, and you divide it by the rest mass of the particle. And it's a dimensionless quantity. And it is a very useful dimensionless quantity. It tells you where you are or how relativistic you are. So it turns out if you're near 1 or greater than 1, you're relativistic. It means you're driving these electrons sufficiently near the speed of light that they have an effect on a relativistic effect. And when you're below that, you are approaching linear. Anyway, it's well used in the field. It's just one of these things. Okay, so this just tells you how big this, I said I was going to show you something about how strong the field is in a plasma, the electrostatic field. So this equation saying Wakefield here, this just gives you a scaling. So this basically tells you, let's say NE were 1/10 to the 18. So that would be less than 10% atmospheric. This tells you that field would be 100 GeV per meter or 1 GeV per centimeter for 10 to the 18. Okay, that's huge. So if you could actually park a test electron in a plasma wave that sees this field, you could have this thing sustained for a centimeter, then you would have 1 GeV. Okay.
So now, when you have this gas jet coming into this vacuum,
I haven't gotten to
does the
that yet.
shape of that?
I'm going to get to the
Okay,
whole gas
all
jet.
right,
I'm giving you the basic principles.
Okay,
And then we're going to have to implement them.
yeah, okay.
We're going to talk about the implementation. But basically, the energy gain you get, this last equation is very important. It is basically force times distance. Force is just the charge. The field on the charge is the longitudinal electric field from the plasma wave. And L is how long can you sustain this force on the electron? You can sustain it as long as the electron is in phase. Once it starts moving it's going to accelerate faster than the laser pulse, right? It's never going to go faster than C in vacuum, but it could go faster than the laser pulse. Once it does that, it dephases. You're in the wrong phase of the plasma wave. So that's what the limitation on the length is. This is just a movie. This actually shows, is this going to work? Yeah, there it goes. So this is actually the plasma wave. It's not really sinusoidal. So the bunch is going to, I pre-populated this with arrows. You see where the accelerated bunch is, it's going to show up here. I haven't even gotten into how you inject, right? I said if you have a test particle and you put it in the thing, I haven't even told you how we do that. That's yet another complicated thing. But let's assume that's happened. And here they are. And you can see them moving left, see this blob moving from left to right here?
Right.
This is in the frame of the pulse. This is in the frame of the pulse. So you can see the fact that it's actually moving within this frame means it's catching up to the laser.
Right.
And it's going to dephase. Let me just run it one more time. So this is the accelerating field.
So all of these dark. are
That's electron
electrons,
density.
And-
That's where they've gone.
And now you're accumulating.
They've accumulated because they've been blown out by the pressure of the laser pulse.
Right.
And then also there's a method of injection called ionization injection. So we've actually seeded this hydrogen with a little bit of nitrogen.
Oh,
And then what we're doing is basically removing the K-shell electrons from helium-like nitrogen. So the 1s2 electrons in helium are just getting loaded into the plasma wave. And that's what shows up here. But anyway, this illustrates dephasing.
Right.
That was the point of this. This is a bunch of math scaling. The point is that this is the key equation, the one on the right. This basically says that in order to get, so there's a trade-off, right? The higher the density you have, the bigger the electrostatic field is, but the shorter the dephasing length is.
and the slower the velocity.
The slower the velocity of the laser is, exactly, which means you can catch up to it more easily.
Right.
So you want to have a trade-off. You can't have too low a density though,
Right.
because then you don't get much of an electric field.
Right.
So the trade-off basically is this equation all the way on the right-hand side, which says that you're optimized if you make the accelerator but the energy gain goes like one, the effect of these competing requirements is that the energy gain goes like 1 over the density. So you're always going to win if you go to lower density. At some point, you can't go to vacuum. So there's a place where this breaks down. But in the range of fractions of an atmospheric density, it's fine. Okay, let me skip through that. Basically, what this says, there's been this, in a lot of fields, there's sort of this milestone number that's floating around. So in the advanced accelerator community, at least the electron community, the milestone number has been considered to be 10 GeV. Why is 10 GeV? Because I guess SLAC was 10 GeV, or a few multiples of 10 GeV. So it was 10 GeV. And so it turns out that to get 10 GeV and to be consistent with not dephasing and having an adequate electric field, you need to accelerate about a meter. In other words, you need to keep that laser focus tight for about a meter.
Wow.
Yeah, for about a meter, which seems pretty tough, right? And you need an electron density about 10 to the 17, which is 1% atmospheric. So you want to be around 1% atmospheric, and you want to guide. I said guide because the only way you can have the intensity in high for a meter is to have a 1 meter long optical fiber.
Mm-hmm.
And now, so our main contribution over many years has been to provide that 1 meter long, or to provide the technology for making the optical fibers. But in the last few years, we've extended that to being able to make 1 meter long optical fibers in plasma densities that are 1% atmospheric. Okay, so now I'm going to, get into the kind of thing you were asking about. Let me get back to that. Okay, so I'm going to skip through this. This is just some numbers about how to calculate what you need for an optical fiber. But anyway, let me just go to this. So many of you are familiar with how a regular optical fiber works. It has a core and a cladding. And the core generally, so there's two kinds of glass or two kinds of densities or something, but your FiOS optical fibers look like this. I don't know if they're graded index or step index. I've drawn what's called a step index fiber, meaning that the center part of the optical fiber, the index is flat, with radius, it's constant. And then it steps down to a lower value out there. So the reason for that, the simple-minded reason for this is that this kind of arrangement promotes total internal reflection. right? If you go from high index to low index and you have a ray at greater than the critical angle, you get 100% reflection. Okay. The other way to think about it is that, light wants to diffract, and the way you beat diffraction is basically when you have phase fronts that curve outward like that. The way you beat diffraction is to force the phase fronts to go the other way. And so the way you can force phase fronts to go their way is to have a slower medium in the middle than on the outside. And something with a higher index means the waves move slower. So this says the center of the beam is moving slower than the outside. That means the phase fronts curve inward, and that cancels diffraction or beam divergence. So that's how an optical fiber works in general. Problem is we need to get guide intensities, 10 to the 7 to 10 to the 8 times larger than that, because glass fiber, if you put 10 to the 11 in there or 10 to the 12, you will destroy it. You need basically a plasma fiber. So basically, this is what we do.
You're gonna get that one way or another.
The plasma fiber.
The plasma, so you might as well start out with the plasma.
That's exactly right. That's why I say if you can't beat them, use them.
Right.
Right. So that's the whole point. The plasma is interesting because it consists of basically free electrons, and ions are in there too. But the electrons are the optically active component because they're lighter and they interact with the laser much more readily because they have low inertia. And so they respond as a negatively polarizable material, whereas bound electrons, which is what you have in a fiber optic, there's no plasma in a regular fiber, a piece of glass. Those are all electrons that are bound to atoms and molecules. So they have a positive contribution to the index. What that means is that to make a plasma fiber, you need a lower plasma density in the middle and a higher plasma density on the outside. That's different than a regular fiber optic. If you were just dealing with the density of glass, you would need a higher density of glass in the middle and a lower density outside. So this goes the opposite way from a glass fiber. You have a lower plasma density in the middle, a higher plasma density on the outside. That's what you want to do. So how do you get that? So the thing that my group came up with many years ago was realizing, this is a particular example, but forget about the word filamenting there. Doesn't matter. Just ignore that filamenting thing. So just imagine I have a long laser focus. Okay. Doesn't matter how I get it. I'll explain how I get it in a minute. But let's just say I have a long laser focus and I focus it down in a gas. And it's a short pulse. That short pulse will impulse heat the gas. It'll ionize the gas, and then it will launch an acoustic wave sideways. So here's a picture. This is from a completely different set of experiments in another area of research that I do in my lab, but the physical principle is very similar. So you make this thing, an acoustic wave leaves, and this is actually experiment and simulations showing that they track pretty well. So this dark red thing is an acoustic wave just moving out sideways. And then if you look a little later, or you look here, there's a density depression on axis, because as this acoustic wave moves out, there's elevated mass in there. And that elevated mass had to be coming from somewhere because mass is conserved. It's a wave. So the mass density is lower on axis. And you can see here, there's a dip. This is all neutral here, by the way. So how do we do this with plasmas? There's something called Bessel beams. This is a way you can get a very long high intensity region. So imagine that I have a plane wave. This is optics, and I hit this cone. This is the cross section of a glass cone. Okay, and you know that light refracts. So when the light ray, I'm looking at the top ray, when it hits that angled face, it refracts downward. And then at the bottom, it hits that angled face, it refracts upwards. And then, but all the way around, it does the same thing in rotation. So imagine this picture in rotation around an axis, basically right through the yellow region right there. What you actually get is a set of self-interfering conical waves. They all interfere. There's interference on this axis. If you actually work out the wave optics of how this looks, it looks like a Bessel beam. Okay, this is what a Bessel beam is. It's a Bessel, it's not really a Bessel function because a Bessel function goes to infinity in the wings. So this is limited by the aperture of the beam. The beam, has its own aperture. But near the axis, this thing looks very much like a Bessel beam. There's a high intensity region in the center, and then there's rings going outside. And if you do the math for this electromagnetic problem, assuming that it's a real plane wave coming in, the solution is a Bessel beam. It is a Bessel function. But we use that. This thing extends over quite a long distance. It's not like it's guiding or something because it is the result of interference. You can see here, that's what it is. But that's all we need. So what we do is extend this thing really far. And we don't use this thing's called an axicon, this conical lens. We actually use the Fab Lab across the street in Maryland to make what we call ring gratings. So it's basically a 0.5 millimeter thick fused silica, plate that's had rulings, concentric rulings etched in it. And they basically diffract. So it's like a regular grating that causes first order diffraction, except the rulings go in a ring around the axis. And so this actually goes through and heats up a gas, causes an explosion, and there's a depression in the center. And that is the beginnings of what we call a plasma waveguide. Okay. We've demonstrated this in what I'm going to show here today. I'm going to show 20. I may actually get up to the 1 meter. I don't know. I may show that in a different slide, but we've demonstrated this up to 1 meter now. Now, I still haven't said what about the gas jet? Where's the source? But so imagine in these pictures, all these optics are just sitting in a chamber filled with gas. So it's fairly clear, right, that we're going to make this hydrodynamic explosion. Which is going to result in shock waves going out, but a single cycle shock wave. It's like an impulse, and then the shock wave goes out, and the density is lower on axis. And so these are some early papers that we did using longer. I won't get into the details, but if you're interested in dusty old history, when you look at the talk, if you download the talk and get it, and you can look at these old papers. But the whole principle of everything I just said was established in these papers from the 90s. It used much longer pulses than we use now, partially because we didn't have the kind of lasers we have now. So I'm going to skip through this. This is what we do now. So this is the ring. So there's a wave coming in, a laser pulse. This is not the thing that drives the accelerator. This is the pulse that generates the plasma waveguide. So there's two pulses. There's one that generates the plasma waveguide, the optical fiber, and there's one that goes down it and makes the accelerator. So what I'm showing here is the one that generates the plasma fiber. And the plasma fiber is basically generated by ionizing hydrogen gas along this extended focus. And we can make various kinds of ring gratings, and we can actually have an element in front of the ring grating called a spiral faceplate. And we can make all kinds of weird Bessel function patterns in this thing. For the experiments I'm going to talk about, all we did was a J0, but we've made J16s, we've made J8s and J5s, but we're going to just stick to this. Basically, I should skip through this. What time is it, by the way?
Oh, well, we're at 2:15.
20 after 2.
20 after 2? Yeah.
Yeah.
All right. Well,
No big deal.
let me skip through this. I'll skip through a bunch of stuff. Basically, okay, here's the experiment. So here's the gas jet right here. So there's two things going on here. One is we basically so here's a mirror, and this beam comes in. There's what we call the ring grating or the diffractive axicon. The beam comes off this mirror and forms one of these Bessel beams above the gas jet. So that Bessel pattern exists all the way along this gas jet, and it ionizes it. What's coming out of this gas jet is a 20 centimeter long supersonic gas sheet. And the Bessel beam just ionizes it. And then the 300 terawatt pulse, which we label as P1, passes through a hole in this mirror and then just guides down this thing. And what squirts out the right-hand side is electrons up to 5 GeV. This was the first experiment. And the numbers work out. If you work out what the electric field is of the plasma wave, you work out the propagation distance, which is 20 centimeters. That simple expression, EZ times charge times E times the phasing length, you get 5 GeV. So it's fairly simple in terms of analysis. I mean, back of the envelope analysis, but you really need to do a very sophisticated simulation. Again, read this paper. Here is the experiment again. So there's a Bessel beam which ionizes this gas sheet, and then we send the 300 terawatt pulse through a hole in this mirror, and it generates the plasma wave, which accelerates the electrons. Page up. 1 second. Yeah, so we've simulated the gas jet. So this gas jet is a non-trivial thing. Again, these have both been submitted already, so I should have updated this slide. But we've done lots of simulations of how this gas jet works and how the Bessel beam interacts with this gas sheet. We've actually even controlled the front of the waveguide by putting a funnel on it. And that's what that picture is. This is our model for the 1 meter. This is not our model. This is our actual 1 meter gas jet. We've used it to make plasmas. I have a picture in another talk here if you're interested in seeing a 1 meter long plasma. That means we have a Bessel beam that shines basically down this thing and generates a Bessel beam pattern all the way down from 1 meter. These are spectra from the last two things. So you can actually see the first experiment goes up to about 5 GeV at the highest energy. Then we have ones from about a year ago that go up to 8 GeV, and the ones from this summer go up beyond 10 GeV. Okay, and in general, what we've done higher energy each time, and we've done slightly lower density each time. Okay, so here's the last part of the talk. I promised to talk about muons. Muons are 200 times the mass of electrons, so their stopping distance is much longer, right? Because the main stopping distance, for charged particles, the stopping distance is controlled basically by radiation, by Bremsstrahlung and stuff. And so if you're much more massive, the stopping distance is much longer. So Louis Alvarez had this idea that one could use cosmic ray muons to image hidden chambers inside pyramids. And there's a paper from 1970. There's a more recent paper updated.
There was a Nova episode on NBC, I think a couple of years ago or something like that.
Yeah.
And I think there was some other team who was doing this again.
Yeah.
With, I guess better
They got
detectors.
Detectors are much better.
Yeah.
The rate of muons wasn't changed, but the rate of detection was enhanced. And so basically, in this particular experiment, they had to accumulate data for 2 years because of the low rate of, I guess, what I say here, 1 to 10 muons per square meter per minute. So it's not a lot. 2 years of data accumulations. Thankfully, the pyramids weren't going anywhere during the measurement. So DARPA was interested in, we don't want to wait around 2 years to figure out if somebody's hiding something. So here's the experiment. So we have a multi-GeV. I didn't get in these are very high charge bunches too that we generate. We're actually getting at least 25% conversion from the laser into the GeV electrons. So it's pretty remarkable. That's another interesting piece of physics that I didn't have time to get into. but it's going to be in our manuscript. We're going to be posting for these things. Anyway, these multi-GeV electrons go in and they hit some converters. This is actually our electron spectrometer. And our slits in the front of the spectrometer are tungsten. And that basically generates gamma rays. And then the gamma rays basically generate all kinds of stuff. There's an electromagnetic shower that produces pions. Ions decay into the muons, as do the gammas do muon pair production. So basically, here's the setup. We simulated this thing. Now we're getting about 10 to the 5 muons per shot. That's enough to do crude imaging. We verified that these are muons by looking at their decay constant. So the cosmic ray muons, about a little over 2 microseconds is the decay time per muons, and then laser muons are about the same. So that checks out. Let me skip this. So here's the experiment. So this is the lab at Colorado State University. It's inside this building. The GeV electrons point along this pink cone here. They rented a truck, and there's a high energy physics group at CSU that did this part of it. We didn't do this. They rented a truck and they put detectors in the truck. So the muons actually went out of the accelerator, through the walls of the building, through whatever, and then into the parking lot, through through the truck. And, it's a basically sealed up truck with these muon detectors inside. And they shielded various selected panels with lead. And they wanted to just see, what shows up as shielded and what doesn't show up as shielded. So here's the picture. So, with lead down there, you just don't see anything. So this is sort of a crude image. It's a crude contrast image. The counts are higher here than where they stuck the lead. So I guess it's all here. So this is really the first imaging done by laser generated muons. So
Big pixels.
big pixels, yes. I think that's it. I don't have a concluding slide, so I apologize for going long. I'm happy to come back and talk about other stuff as well.
Okay.
I take it muons are also dangerous. You don't want to get in the middle of a muon beam because of all the lead.
So the lead is used to filter out everything and let the muons through.
Okay.
So the detection of muons is basically a process of elimination. Basically, you basically do simulations.
Can you see that?
Whatever gets through is
Because you have lead shielding, so I figured.
the lead shielding is basically, you have a lot of other dangerous stuff. So you have high energy electrons, you have gammas.
Okay.
I mean, it's really gammas. So the electrons go into this thing and they just generate, the gammas, and then you have nuclear activation from the gammas as well.
Yeah. Okay.
Photoneutron.
All right. I see what you're doing. So I guess the question is this, I guess, applicable only to electron accelerators? I guess,
Yeah.
I guess I'm thinking of like the CERN people. They're already thinking ahead to the 2040s. But the only thing they got going now is maybe an even bigger ring of what, 100 kilometers diameter or whatever. Will this help maybe produce some other way of building a large accelerator cheaper or more?
Well, so this is directed to electrons. So this would, go towards an electron-positron collider.
Okay.
But it would not go towards a hadron machine.
Okay.
Because they're just too massive, and so the inertia is just too big.
Okay.
This works because the pulses are short. They need to be short to get the intensity up, to get those electric fields. But because they're short, they're not sustained enough to accelerate protons, essentially. That way. Now there is a way of accelerating protons, and it's a big field. but they're not at the energies that you would be interested in for high energy physics, but they are of interest, for instance, for proton therapy. And so it turns out that if you hit a thin foil with an intense pulse, and it's a short pulse, so the foil doesn't blow up or anything on the time scale where the pulse is going in, it will generate inside the material, inside the metallic foil, it will generate a lot of very, very energetic electrons, because those are the things that respond most quickly to a short laser pulse. And those electrons actually can be heated to temperatures of MeV, They will then diffuse to the far side of that target and exert a tremendous pressure to leave, to just blow out, and they will pull ions along with them. Turns out in the early experiments, there was enough water contamination, and it's hard to get rid of water on surfaces, but there was either water or there was hydrocarbons, from their vacuum systems on these surfaces. And this very intense beam of electrons, which was trying to escape the surface, would basically ionize the surface atoms and pull the protons off because they're lighter.
Yeah.
And some of the other stuff would lag behind. And so people saw these beams of protons coming out of these, things. Now, the energies of these are no, they're tens of MeV kind of thing. They're even too low. Somebody on the listening may know better than me, but for proton therapy, you need 100, 200 MeV protons, something like that. And I don't think the lasers have gotten to that yet. They may, but the lasers are rather big for the purpose. But I don't think they've gotten to 100, 200 MeV.
Charles has his hand up for a question.
Yeah.
Yeah. So
Hello, Howard.
Hello.
Long time since we were working together in Princeton.
Wow. Hi, Charles. How are you? You look the same.
Yeah,
As far as I can tell on the tiny postage screen.
yeah. Glad to hear the business is doing well. And congratulations on all the good results.
Oh, thank you. Are you at the lab now or are you at home?
I'm at home.
Oh.
I actually I retired a few years back, but I'm still writing books and contributing to paper. Yeah.
That's great.
Yeah. Good. Thanks.
Oh, you're welcome. Nice to see you.
Yeah.
Are
Charles,
there any
what's
other
up?
questions?
Okay.
Please
Dick, is Dick
unmute.
Hubbard still there? You can ask another question. Maybe he got off the phone because he saw the top one too many times.
Well, we had a big interest out there. I think 16 people or something like.
Oh,
Or
is that good? Is that good?
that's good.
Okay.
Very good.
All right.
No, we very interesting presentation. I loved it very. I mean, it educated me a lot on the whole mechanism here and the kinds of things that you're having to contend with to get this beam
These are
after moving.
these are very complicated experiments.
Yeah.
They're not, and as I said, students really benefit from this. And it's exciting to do. They're not sitting at a computer terminal. It's very kinetic and very active. Because you got to manage the lasers, make sure that's going. There's a vacuum system. The thing I didn't mention about limiting the rep rate is that we're puffing an awful lot of hydrogen into the vacuum chamber, and it takes a long time to pump it out. So that limits. So it's not that. The laser is 1 hertz, the one at Colorado State University, but we're only able to run 1/8 or 1/16 of a hertz because it takes that much time between shots to pump all the hydrogen out of the chamber.
But you have hydrogen coming out of the metal anyway, don't you?
Yeah, but that's negligible compared to
Okay.
to this. We back these valves with multiple atmospheres, right? So, yeah.
You also
What's the radiation problem? Is there a radiation problem in the room? Do you have to go out while you're using this? Accelerator?
Yes, this is very interesting. We at first had a lead shield between the chamber, big lead wall between the chamber and the control computers and everything. But this was just based on our own calculation. But at CSU, they were just getting in. This is the first time they did an experiment like this at Colorado State University. So everyone was going by the seat of the pants, but they sent their radiation safety person over. And the situation now is that we ran all the cables from that room over to a control area in a different part of the building. So yes, radiation is a serious issue. There's another really interesting thing that happens as well. There is a gigantic EMP that happens when you send that few hundred terawatt laser into that plasma waveguide. It is, and this initially when we were doing these experiments, it blew out a lot of our stuff, blew out our cameras, blew out our motion controllers. So now before a shot, we unplug everything. It's sort of a crude way to proceed, but it saves us, time and money. So there is a really serious EMP. In fact, I called one of my former students who's working on this EMP problem at Air Force Research Lab, who is sort of interested in purposely generating these kinds of EMP things. So she sent her people with their high bandwidth scopes and antennas to sort of measure what's going on. So yeah, so it's a bother, but it's really interesting physics as to what causes this giant EMP. Yeah.
Yeah. Wow. Any other questions then? Well, I want to really thank you for a fantastic presentation. Enjoyed it very much. And
Thank you.
And
It's a pleasure.
Thank you for coming.
oh, thank you.
Pleasure.